Okay, everybody, so now we're going to actually apply some of the ideas we talked about in the previous video to look at how we actually go through the procedure of doing inference tests on population proportions. So what I'm going to try to do with this video is, as clearly as possible, explain the different steps that we take, explain also how those steps connect to the philosophy of science and why we use the language that we do and the processes that we do, and finally go through two examples to give you an idea of how this process will look and how we end up drawing the conclusions that we do and how we end up connecting everything. So first, let's talk about the difference between a confidence interval and doing an inference test. So we will do a confidence interval if we don't know the parameter, but we would like to estimate it. So if we just have no idea what a population proportion would be, what percent of people really like chocolate ice cream, I don't know, just think off the top of my head, we would do a confidence interval. When we do a confidence interval, we end up deciding on a confidence level that we want to use. Like we saw last time, 90%, 95%, 99% are very common, but that ends up being a decision that we make as a statistician. But what if we're given a parameter and we want to test it? So instead of having no idea what it might be, we're told what it is, but we're not sure. There's something we want to compare it to. That's when we do an inference test. And when we do an inference test, we end up deciding on what we call an alpha level, which we talked about in the previous video. That's basically how low do you need the probability to be before you end up rejecting the null hypothesis. So let's go through the general methodology for an inference test. This is the methodology we'll be using when we do our examples. Now, I want to point out that many aspects of this process are used on any inference test. What's going to change is the actual numbers and how we find them, but the procedure should be very similar. So we always start by defining our null hypothesis, which we call h sub 0. For proportions, that's going to be whatever the default parameters that we're given. Whatever we're told it actually is, whatever we're testing. We want to then define our alternative hypothesis, what we think might be going on. We also should determine the alpha level we're going to use. Now, normally we're going to give this to you in the problems, but this is something the statisticians have to decide when they do tests. And they should always decide ahead of time so as to not look that they're trying to use what we call hindsight bias and skew the results. So before we actually do the test, we're going to get a statistic. In our case, we're going to get a sample and get a p-hat from that sample like we did with confidence intervals. And we're going to get that for a certain sample size. If we sample 50 people, 100 people, 1,000 people. We then need to determine the mean and standard deviation of our sampling distribution. Now, we did this a couple lessons ago. All right, so but I'm going to be reminding you how we do that. For proportions, the mean is going to be p, the original parameter we're given. Notice it's not the one that comes from our sample. This is because we always assume the null hypothesis is true. This goes to that idea of avoiding confirmation bias. We're going to assume that we're wrong. That's how we begin good science. The standard deviation of the sampling distribution, if you recall, is the square root of p times 1 minus p over n. Again, I'm going to say this once more. That's based on p, not p-hat. And I'm saying that because that's a common mistake here. We're basing it on what we're told the answer is, not what we got from our sample. From there, we use normal CDF to find the probability of getting a p-hat at this value or one more extreme, and through the examples you'll see what we mean by that, using the mean and standard deviation we just found. That probability is called our p-value. Now, for proportions, that's a little confusing because we use a p for proportions as well. But we use p-values for all inferential statistics, and when we say that, the p in p-value means probability. Everything we're talking about is about probability. So ultimately, what you're going to end up deciding is whether you're going to reject the null hypothesis or fail to reject the null hypothesis. If the probability you find using normal CDF is less than your alpha level, then we will reject the null hypothesis in favor of the alternative hypothesis. Notice the italicized language there. If our probability is not less than our alpha level, then we will fail to reject the null hypothesis. Now, this is very important language. We're not actually proving or disproving anything. We are not finding any statement to be true or false. We're using probabilities here, not absolutes. When we say for example, if we fail to reject the null hypothesis, we don't have evidence that it's wrong. That doesn't mean we accept the null hypothesis. That doesn't make it true. Everything here is about the probability of something happening. When we do these tests, we're not saying anything for absolute certainty. And if you recall from the last video, science isn't about knowing things for absolute certainty because we don't assume we ever can know things with absolute certainty. As soon as we do, we open up the chance that we're wrong. So you're going to see what we mean by this and what this looks like in context. And I want to really emphasize this because the worst thing someone doing statistics could do is to come away saying that their test has proven or disproven something. That's never what we're doing here. We're finding evidence for or against. We're rejecting, which means not saying it's false. We're just favoring a different hypothesis. Something is more likely to be the case. And we're never accepting. We're not proving true or, well, we couldn't prove it false, therefore it must be true. If you go back to the coin example from the past video, no matter how many heads you got in a row, that process was not sufficient to prove whether or not that coin was fair or not. You just had evidence for or against. Either way, you weren't sure. So I've beaten that to death. But let's actually take a look at an example. So I apologize for the topicality of this example, but it's what I thought of. I promise the second one will not be so topical. So an internet article says that according to a national poll, 63% of all Americans are in favor of extending the quarantine to abide by the advice of health experts. You also read in a local article that a poll of 1,000 random Connecticut citizens found that 674 are in favor of extending the quarantine. Notice that's a higher proportion than the 63%. Do you have significant evidence at the alpha equals 0.05 level, there we gave you alpha, that the true proportion of Connecticut citizens in favor of extending the quarantine is greater than the reported national proportion of 63%? Another thing I want you to just real quick notice here is that this is a wordy example, but most problems like this are about this wordy. So a lot of these statistics questions require a decent amount of reading to get the information that you need. So you need to be mindful of that when you approach these problems and don't get intimidated by it. So let's actually do the process and the computation that's required. So the first thing we're going to do here is define our null hypothesis. And according to the problem, the null hypothesis is that the actual proportion is 0.63 or 63%. We always put it as a decimal here. We generally don't write as a percent when we're doing this formally. From there, we're going to do the alternative hypothesis. And according to the language of the problem, we suspect that the true proportion of Connecticut residents is greater than this. So our alternative hypothesis is that the true proportion is greater than 0.63. From here, we also see in our problem that out of our 1,000 people surveyed, 674 would prefer to extend the quarantine. That's our p-hat because it came from our sample. So that's equal to 0.674, which is 674 out of 1,000. From here, we're going to define the aspects of our sampling distribution. The sampling distribution should have a mean of p, which is 0.63 here. And it should have a standard deviation of square root of p times 1 minus p over n. Now, for that, we're going to get out our calculator, and we can do it here. So we want to actually do it out to see what it equals. So it's going to be 0.63 times 1 minus 0.63 is 0.37, and that's divided by 1,000. And that comes out to about 0.01526, or I'm just going to say 0.0153. And I'm going to round it to 4 decimal places. From here, this is where we do our normal CDF. Now, for a normal CDF, we need a left bound and a right bound. And this is where we're talking about getting a p-hat of what we got or more extreme. So the p hat we got was 0.674. What would more extreme than that actually be? Well, since we're considering that the proportion is greater than 63%, more extreme would be higher than 0.674, further away from p. So my left bound is going to be 0.674, and my right bound is going to be essentially positive infinity, which I'm going to put in as E99. We put in our mean of our sampling distribution, which is 0.63, and our standard deviation is 0.0153. So on my calculator, I'm going to go into inverse normal CDF, and I'm going to put in E99 for my left bound, or sorry, 0.674 for my left bound. My right bound is E99. My mean is 0.63. And my standard deviation is 0.0153. I'm going to paste that. And we end up getting 0.002. So now that we know it's 0.002, we can see that that is indeed less than the alpha that we specified of 0.05. And because our probability that we got is less than our alpha, we say that we reject the null hypothesis of p equals 0.63 in favor of the alternative hypothesis, p is greater than 0.63. Notice I'm not actually saying what I think p is, I'm just saying that we're rejecting the null hypothesis in favor of the alternative hypothesis. Another way that we could say this is that we have significant evidence at the alpha equals 0.05 level that the true proportion of Connecticut residents in favor of extending the quarantine is greater than 63%. We're not making a claim right now of what it actually is. We're also not saying that we know the true proportion is greater than 63%. We're just saying that we have strong evidence, significant evidence that it is. So again, that's that whole we're not making an absolute claim, because as soon as we do, we open up the chance that we're wrong. All right? So let's take a look at another example. So I promise this one would be a little less topical. Perhaps a bit more tropical. Sorry. So according to Peachwave's website, the most popular flavor of frozen yogurt sold at their locations nationwide is strawberry. They claim that 44% of all customers have strawberry as their favorite flavor. You suspect that strawberry is not that popular in Brookfield. So you sample 60 randomly selected Brookfield Peachwave customers and find that 21 of the 60 said that strawberry is their favorite flavor. Do you have significant evidence at the alpha equals 0.05 level, we're using 0.05 again, it's one of the most common alphas anyway, that the true proportion of Brookfielders who prefer strawberry is less than 44%? So in this case, notice that our alternative is the opposite direction. We don't think it's more than 44, we think it's less. And maybe it's because you have a lot of friends that go to Peachwave and they say that they don't prefer strawberry, and if you recall from the last video, that would be using the availability heuristic. Just because the information close to you says that doesn't mean that's actually true. So let's go through the actual process of how we would do this test. So again, we start with our null hypothesis, and if you've been following along, you should predict that the null hypothesis should be that p equals 44%, or 0.44, whatever we're told it actually is. Our alternative then is, in this case, that p is less than 0.44. We think that the actual proportion is less than that. So now we have to get our p hat. And if you're not sure about p hat, you can bring up your calculator, and we found that 21 out of the 60, which gives us a p hat of 0.35. So p hat is 0.35. Now we're going to figure out what our sampling distribution should look like. It should have a mean of p, or 0.44, and it should have a standard deviation of the square root of 0.44 times 1 minus 0.44 over 60. And again, we'll get out our calculator to do that. So square root of 0.44 times, if you know that that 1 minus 0.44 is 0.56 out of 60. And that's going to give us a standard deviation, looks like 0.06408. I'm going to round that to 0.0641. All right, I like 4 decimal places. But now we're going to do our normal CDF. Now it changes a little bit here because, again, what does more extreme mean in this case? Since we're considering values less than 0.44, more extreme would be less than our p hat. So our left bound is going to be negative infinity, essentially, in this case negative E99. Our right bound is 0.35. Our mean is 0.44. And our standard deviation is 0.0641. So once again, I'm going to go into my calculator, go into normal CDF, and now we're just going to put in our new values, negative E99. Our upper value is 0.35. Our mean is 0.44. And our standard deviation is 0.0641. And let's see what this gives us. This gives us a value of 0.08015. So I'm going to say that's about 0.0802 just to keep to the 4 decimal places. Now one thing we should see is that that is greater than 0.05. So in this case, our probability came out higher than 0.05. And when that happens, we must fail to reject the null hypothesis of p equals 0.44. And again, just to hammer it home, we're not saying that that means that p is 0.44. We haven't proven that. We don't accept it. We're just saying we have failed to reject the idea. So we failed to reject the null hypothesis of p equals 0.44. And like before, I'm going to give you another way of saying that. We could say that we do not have significant evidence at the alpha equals 0.05 level that the true proportion of Brookfielders who have strawberry as a favorite flavor is less than 44%. Now, you might think like, but in our sample it was less than 44%. And that's true. But you have to consider we sampled 60 people. And assuming we got a good sample, it could be that just in that sample it came out to be 35%, but that doesn't necessarily mean that the true proportion overall, if we sampled everybody who goes to Peach Wave and Brookfield, that it would be less than 44%. So we're being, again, very careful with our language here. So those are our 2 examples of how to do an inference test on proportions. I hope this made sense, and we will see you guys next time.